Hi guys, welcome to Safi Mixed. In this video, I use Newton's second law to study the dynamics and the trajectory of a particle under a special condition. And the special condition I'm using is that the net force F net acting on the particle is zero. Yeah, this is the most simplified case or the most simplified application of Newton's second law, the easiest one. However, this will give us an insight how to use the differential form of Newton's second law for studying the dynamics and the trajectory of particles. And under this special condition, we reduce the mathematical form of Newton's second law to obtain the statement of Newton's first law. So there are three targets in this video. The first, I'll find the dynamics of the particle under this condition using Newton's second law, and will establish an equation for the trajectory of the particle, and then will use my results to compare the output of Newton's second law under this special condition with the statement of Newton's first law. So in order to simplify things, I consider the motion along one direction, preferably along the x-axis of Cartesian coordinate system. However, the results that I write here can straightforwardly be replicated for y and z direction. Those results can be put to formulate the vector equation for the physical quantities that I'm deriving here. So to begin with, I consider the differential form dv sub x over dt equals f of x divided by m. This is one of the differential forms of Newton's second law, and you see the subscript here I'm using to emphasize that we are dealing with one directional motion. And for simplicity, I can drop that, and for mathematical easiness, I can drop the subscript. However, that will be in mind that we are dealing with what direction, and that's the reason I'm not putting the vectors notation on velocity as well as force. So using this condition, that is the net force acting on the particle is zero, then this side of the equation reduces to zero, and I can write this as dv over dt equals 0. Note that I have dropped the subscript x. However, I'm not putting the vector notation. That means I'm dealing a one-dimensional motion or with one-dimensional case. Now, I can straight away write this equation in the form dv equals 0 times dt equals 0. And this is now the most simplified differential equation that I can integrate, provided I know about the initial and final velocity or about the boundary condition or initial condition of the differential equation. So I suppose that initially the velocity of the particle is vi, and at any time t later, which we call final velocity, is vf. With these values of the velocity, I can integrate this equation straightforwardly to write it in the form dv with vi to vf equals 0. And we know from the formulas of integration that the output or the result of this integral is in fact velocity v. So I can write v from vi to vf equals 0. And if I put the limits, I can write this as vf minus vi equals 0, or I can arrange this to write vf equals vi, and since the initial velocity is a constant for the rest of the motion, therefore I can write this as constant. This result is in fact the statement is part of the statement of Newton's first law, which states that a body will move with uniform velocity at the velocity of the body will remain unchanged in the absence of any external force. Or another, if the net force acting on the particle is zero, the velocity of the particle remains constant. So that is the first part of the statement of Newton's first law. Now, I can play with this equation a little more to find the trajectory of the particle. Since we know that the final velocity or the velocity at any time can be written as the derivative of position with respect to time, and I write this as Vi. Or I can arrange this equation into the form dx equals Vi times dt. And again, if we know about the initial and final positions of the particles, then I can integrate this equation, and I suppose that initial position of the particle is x sub I at initial time t sub I, and x sub f at final time tf. Then integrating this relation, I can write integral from xi to xf dx equals, since Vi is constant, therefore I can write that out of the integral and can write it Ti Tf dt. This is very easy. The result of this side is x with limits Vi to Vf equals Vi and t with limits Ti to Tf. And if I substitute the limits on both sides, I can write, oh, this is not Vi, this is in fact Xi, and this is also Xf. So I can write Xf minus Xi equals Vi times Tf minus Ti. Or I can put this equation into the form xf equals Vi, this is the duration, and I write this as delta t, and this minus to this side would become plus xi. Now this equation defines the trajectory of the particle, and you see this in fact is a straight line equation in the position and time plane. That is, if I want to plot this equation in a position time plane like this, I take the x-axis along, or the position along vertical, and the time along horizontal, then this is an equation of the form this, where this is the position intercept equal to xi, and this Vi is in fact the slope of this particle, which is delta t to delta x, or I can say that the slope V is raise delta x to the run. So this is in fact a straight line equation in the position time plane with slope equal to the initial velocity Vi. So that means in the absence of external force, the statements of, so that means in the absence of external force, the form or the mathematical form or the differential form of Newton's second law reduces to the statement of Newton's first law, because in the first equation we see that the velocity remains constant, and in the second equation for trajectory we see that this is a straight line equation, and that was Newton's first law state that in the absence of external force, a body will move with uniform velocity along a straight line, and this is the straight line. At the end, if you haven't subscribed to Safi Mix, kindly support the channel by pressing the subscribe button and also the like button on the video. Thanks for watching.